So we're going to be speaking today, covering chapter 26 of the textbook. So if you're interested, there will be more details there. Just as a reminder, homework 6, the programming portion, is due tonight at midnight. And if you have any questions, we have TA hours this afternoon after class. I'm also available after class if you need any help with anything. The final, once again, is this Friday in this room from 12:15 to 3:15. Please let us know if you have any concerns about that time or just studying or anything you want to talk about at all. So let's return, just as we start our kind of summary discussion, back to the beginning of the class where we talked about what is AI, what is artificial intelligence. So the book basically defined it as a discipline that systemizes and automates intellectual tasks to create machines that do one of these four things. And we talked a little bit about the differences here. So you can have either acting or thinking like humans, and acting and thinking rationally. And so we've seen, I think throughout the quarter, the acting rationally was the definition taken by the book, and that allows us to apply kind of formal and mathematical methods to deciding which actions an agent should do, and what is kind of the right thing to do in a given setting. We've seen several achievements of AI, and I hope the videos we've seen throughout the quarter have been illuminating in this regard. So we've seen things like logical reasoning systems, search and game playing, chess and checkers games, knowledge-based systems. We've seen how Bayes nets can be used to diagnose system failures and other things. We've seen applications of machine learning, so in the helicopter flying and stuff like that. Also in planning and dealing with logistics of large number of military components in a military system. And also, a lot of the applications we've seen have been autonomous robots, from autonomous wall climbing robots to autonomous car driving robots to everything in between. So, we've seen helicopter flying, car driving in the real world, and all the things it has to deal with. Robots that are working together as a team to play soccer. Constraint satisfaction in robotics being applied to actually help people overcome cancer and things that they have to deal with in their real life. So this kind of concluding chapter takes a more philosophical view of some of these AI topics we've been discovering. And at a high level, there are two kind of different views on AI, and they're generally called the weak AI hypothesis and the strong AI hypothesis. So weak AI is more concerned with the question of, can machines act intelligently? So they say, we're not really going to worry about, can machines actually think, but we're just going to focus on, can we get them to do intelligent things that are useful? And so the weak AI hypothesis is that we can do this. We can get machines to do things that are intelligent looking. The strong AI hypothesis goes a bit further and says that we can actually get machines and computers to think and actually understand and comprehend things like this. So we're going to look just briefly at a few topics and arguments about each viewpoint. There's more details in the book about each of these. So, starting with weak AI, there are some philosophers and people, especially if you go back 10, 20 years, who argued that AI is impossible. And that really depends, I think, on how you define artificial intelligence, right? So the view we've taken in the book is basically that artificial intelligence is the quest to find the best agent program for a given problem on a given architecture, right? And if we define it like that, then clearly it's possible, because for a given architecture, we only have so much memory, we can only configure it in so many different ways. So there's a very large but finite number of different programs we could have. And so out of those, one of them will be the best, and we can achieve it, right? Theoretically. And this question of can machines think? There's some that argue, and the book, I think, correctly says that maybe this isn't the right question. Our terminology and our language gets in the way of us understanding sometimes, right? So if we ask the question, can airplanes fly? I think everyone would say, yes, they can fly. Do they fly the same way as birds? Well, no, but I mean, they don't flap their wings, but they're getting up in the air. If we ask, can boats swim? In English, most people would say, no, boats can't swim, because swimming has connected to it just, the use of arms and legs, or kind of your body to propel yourself in the water. In other languages, it might be different. The book points out that in Russian, boats swim just like humans do, just from the usage of the word. And so the book kind of points out that this whole idea of that machines could possibly even think has only been around for such a short time that our language hasn't really adapted and kind of come to a definition of what think actually means. Like, if think just means using your brain, then machines can't think. But if it's a more broad term, then it's possible. So the Turing test that we saw at the beginning of the class really focused the discussion. He thought it was, not very productive to talk about can machines think, but rather let's take some intelligent behavior and focus on that and see whether we can get machines to do it. So the book points out some possible objections to the possibility of intelligent machines, and we'll just talk about a few of those. The first is called the argument from disability. And so this was discussed by Turing in his first paper, and so it's basically just saying, well, a machine could never do X, so therefore a machine can never do some of these intelligent behaviors. So some of the things Alan Turing listed from his paper are things like a machine can never be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries and cream, make someone fall in love with it, learn from experience, use words properly, be the subject of its own thought, have as much diversity of behavior as man, or do something really new. And I think throughout this class, some of those we haven't really touched on at all, obviously like the falling in love and enjoying strawberries and cream. But learning from experience, we've seen some simple cases where agents are able to learn from experience. Use words properly. There's definitely a whole field of AI devoted to getting machines to be able to use natural language in a meaningful way. And also, many things that previously were thought to require high levels of human intelligence, we've seen that machines can attack these problems, like chess, checkers, drive cars, fly airplanes, diagnose diseases, discover things, and even use judgment. So the book points out that a researcher looked at 20 studies where experts were trying to determine things like what the chance, or whether a criminal, when released from prison, would eventually end up back in prison or not. And he found that simple kind of statistical learning methods were able to do better than the experts on a lot of these questions like that. And so now hopefully you can see kind of a little bit of behind how a chess program works. It's exploring all the moves it can do and using alpha-beta pruning and an evaluation function. And these aren't necessarily the same ways that a human might go about it. A grandmaster sort of looks at the board and it just seems to shout out to him what the right move is in the situation, and he's not necessarily consciously going through all these different options. And so the weak AI really focuses more on the behavior instead of kind of how the behavior is performed. Another possible objection is more mathematical. So you're probably familiar with the fact that there are certain mathematical questions that are unanswerable by formal systems. So when you talk about decidability, so there are certain questions that, say, Turing machines can't answer. And Gödel's incompleteness theorem is another example of this, where there are certain statements that a formal system cannot prove. Is this necessarily a bad thing? Because most people sort of intuitively argue that people aren't restricted by these things. But if we take a sentence like this, Bob cannot consistently assert that this sentence is true. Well, this sentence is in essence restricting Bob's ability to prove it, right? Because if Bob asserts that this sentence is true, then he's asserting that it's not true by the content of the sentence. And if he asserts that it's not true, then there's something that he can't assert as true, right? So we've somehow limited the ability of Bob. But we don't think any less of Bob because he can't assert that that sentence is true, right? So maybe this mathematical objection, maybe agents, we shouldn't think any less of them if they're restricted in certain ways like this. And a lot of the times when people use these types of discussion, it's possible to take a formal system like a Turing machine or a formal logic and say that, prove rigorously that it's impossible for it to prove the truth of some statement X. But then for the flip side, we say, well, intuitively speaking, humans are able to do X, right? But we don't have any rigorous proof about our own ability, because to do that we would have to have some formal model of our own ability, which would then kind of inevitably not fit all of the ability that we have. So moving on briefly to strong AI. So the point made by some philosophers is that even if a machine could pass the Turing test and exhibit this intelligent behavior, it still would only be simulating this thinking. And the book, one interesting thing it points out is maybe we're holding these computers and robots and agents to a higher standard than we hold ourselves, right? So presumably all of us are self-conscious, we think about ourselves and our own thoughts, and we have this feeling that we're thinking, right? But throughout our lives, none of us have direct evidence that anyone else is doing the same thing, right? For all we know, everyone else could just be figments of our imagination or, automaton. And I mean, there's certainly science fiction movies and books that explore these types of possibilities. And, there's a lot of mystery around topics like this. And one thing Turing points out, which I think is very, very important, is that a lot of these things, they really don't affect our ability to build useful systems, right? Whether the system is actually thinking or not doesn't really matter if it can do something useful that we want it to do. And there's sort of a general question that arises in a lot of these cases is, when we can artificially create something, is that thing real? Is it the thing that it's supposed to be? So there are some things like artificial urea and artificial sweeteners and artificial insemination where the artificial thing is just as real as the other thing, right? As the non-artificial thing, that it performs the task that's desired of it. But there are definitely other areas, like if we have artificial flowers, well, they're not real flowers, they're not going to die, right? Artificial wine, if you produce in a lab some wine that's supposed to be from some remote valley in France, it's not the same thing, right? Because it's not from the remote valley in France. And the thing people pay the money for and that they desire is, the knowledge that this wine was grown, that it came from this specific place. If you artificially create a Picasso painting, it might be an exact reproduction, but it still won't be a Picasso painting because he didn't create it, right? And so these are some of the things that, just topics that are related, right? So sometimes the behavior of an artificial thing is the thing that's really important, and sometimes it's more the pedigree. Where did it come from? And those are actually the things that let us know if it's actually, if it can actually be the exact thing. So the question is, where does thinking and intelligence fit in the spectrum? Does it matter more where it actually comes from, or just what the final behavior is? And one of probably the most famous thought experiments addressing some of these things is called the Chinese room, that we'll just talk about briefly here. And it was devised by John Searle in 1980. So the general setup is this. We have a room without any doors or windows. It just has a slot where people can put in slips of paper and a slot where the person inside can slide out pieces of paper. The person inside understands only English. The room has lots of books in English that have rules, so you can read them. It has lots of paper, writing utensils, and maybe some Chinese symbols in these rule books. So this human, a paper is passed into the room, and there's Chinese writing on the paper, so Chinese symbols. The person has no idea what they mean. But he can look up in all of his rule books, right? And he can say, oh, if this symbol and this symbol appear, then I should write this symbol on this piece of paper. And basically he's executing some sort of a program with these rules. And so then as part of this, the human will create kind of an output piece of paper with Chinese symbols on it. He once again has no idea what they mean, but then he'll slip it out the outside. So Searle says that this setup, with the right books and the right human inside that could follow all these instructions, it could presumably pass the Chinese Turing test, right? So you could have Chinese people slipping in questions or conversational tidbits on paper, and then this room would output an appropriate response in Chinese. And so from the outside, we have this concept of the room understanding Chinese, right? It's passing the Turing test. You can communicate with it in Chinese. But if you look inside the room, there's nothing that understands Chinese in the room, right? So the person, it's given that it doesn't understand Chinese. And Searle argues that the paper and the book, well, they're just things they can't understand. And so there's no understanding of Chinese in the room. And so he argues that this basically is exactly the same setup as with a computer, right? You have a CPU, it's executing rules, it doesn't really know what the symbols mean that it's manipulating. And so even if it could pass the Turing test, it wouldn't necessarily have understanding. So now we'll move on just for a couple more minutes before the end of class, talking a little bit about the ethics of AI in the future. So there are several problems, kind of ethical questions that AI poses. From the fact that people might lose their jobs to the automation, right? If we have autonomous robots or just robots that can do things, they might take away people's jobs. I think we've seen this already with a lot of industries. People might have too much or too little leisure time. I think this was we've definitely seen a change in the way leisure time exists, basically, over the last century or so. As robots get more abilities, people might lose their sense of being unique. They also might lose some of their privacy rights, right? As we have autonomous robots that can watch you and figure out what you're doing, and kind of this big brother idea. An interesting one that we'll delve into a little bit deeper is the use of AI might result in a loss of accountability. And we'll talk about this more in a second. And there's some that fear that the success of AI might mean the end of the human race. Right? So these are big questions. Delving into the loss of accountability, there's a lot of questions. If we have autonomous AI systems, right? So if you have an AI diagnosis system for a doctor, and it comes up with some diagnosis, and the doctor follows it, and the patient ends up dying, who's at fault, right? Is it the doctor's fault? Or is it the guy that programmed the Bayes net? Or is it, Bayes himself because his probability rules didn't work in this case? Who can we blame? What if you have some trading agent that you program and you accidentally put a bug in it or something, and it incurs a ridiculous amount of debt for you? Is it your fault? Are you liable for this debt? If we have autonomous cars driving around in the future and a car wrecks or kills somebody, does the insurance cover it? Who has to pay for it? There's a lot of these types of questions that have not been answered. And I think our laws haven't quite caught up with some of the capabilities that we've seen exhibited throughout the class. And also, and this is kind of my personal feeling, is that our society also has a ways to catch up with some of these capabilities, right? So for example, if we think about humans flying a plane, every once in a while a plane will crash, right? And we're fairly forgiving as a society to human errors, right? So if it's a big storm and it was really hard to fly the plane and there was low visibility and it got hit by lightning and whatever, and the pilot, tried the best he could, but the plane crashed and some people died. We all understand, right? He did the best he could. It was a hard situation. But if you think about, if we put a computer program flying a plane by itself, what types of errors would it exhibit? And if you think about lots of your computer programs, if you have a little bug in, it might ignore its sensor input or something, and just do something really ridiculous like fly into a mountain in broad daylight, something a human would never do. And if we ever get to this point, how is society going to react to that, right? And I think if something like that happened right now, it would be, we're never going to put AIs in charge of flying planes ever again. We're just, and they're going to close down the business that sold it and put the, airplane company that put this program in charge out of business, and this would just be a total disaster. Whereas if the AI messed up in a human-like way, maybe we would understand. It's just we can't understand the mistakes that an AI might make. And as a last point, kind of AI and warfare. So we already have, autonomous or near autonomous systems, flying around and dropping bombs on people and things like this. And this just opens up a whole lot of ethical and moral questions, and even practical ones, right? So if a drone or some autonomous airplane drops a bomb on the wrong city, whose fault is it? Is that a war crime for the programmer? Does he have to go to jail for that? How does it affect soldiers when instead of, even on where they're remote flying these drones, is there a big difference from, you go to the office and you're flying drones and dropping bombs on people with a joystick, and then you go home to eat with your kids? Maybe that's even more stressful than being in the, in the jungle fighting against these people. Who knows? And as a programmer, if you're writing code that has to somehow distinguish between, a small innocent child and, some enemy combatant, because you're writing the software that this robot's going to use to decide who to shoot, that's a huge responsibility. And how does that affect? Maybe some people wouldn't even want to touch that type of a program, right? And so, some of these questions are a little bit definitely unanswered, but there's lots of questions out there. So in conclusion, my own personal feelings on a lot of these topics are basically the AI, and we've seen throughout the course, AI gives us a lot of tools to solve lots of different problems, but how we use these tools depends on us, right? Like any tool in the wrong hands, it can be used for the wrong purposes. But coming back, I guess, to this class and my goals from this class, I hope that from what we've talked about, you'll be able to use AI techniques to solve problems you might come across in the future, or also understand new things that come out. If you come across things that make radical AI claims in the future, you'll be able to understand them better. And also, if you're interested, to just inspire you to look deeper at some of these topics. I think the whole book is full of really, really cool topics, and there's lots of interesting work being done in AI today. And hopefully we've sparked your interest enough to continue on it. So thanks for being part of the class. Okay, so we will have a video, our last video, and then have a short break, and then the rest of the class today is just open for your questions. And I think we'll try to answer them on the board, so hopefully people out there and watching online and stuff can get the input too. But as soon as we're out of questions, then we're done, and John will have office hours this afternoon. I'll be available as well, and it's just on to the final. Okay. So this video is from 1969. It's a video about the history of computers from kind of a British perspective. And it's just kind of interesting, say some interesting things with regards to a lot of these topics we've been discussing. So.
More and more people are coming into everyday contact with computers. In thousands of banks, computer terminals are taking over much of the clerical and accounting work. Relieved of most of the clerical drudgery a smaller and more intelligent staff can spend more of its time on the interesting and human job of dealing with customers. The man on the shop floor can already be in instant communication with the computer. And the day is coming when the computer will carry out unskilled manual jobs as it has already taken over unskilled clerical ones. With more computing power, we shall cease to waste people on low-grade manual work and find better uses for human talents. Some young people are already being taught by the computer. A generation is growing up which will find the computer terminal as familiar as electric light or the telephone. And we are only just at the beginning of the computer age.
Well, I suppose computers are all right, but I don't know what all the fuss is about, because they're not really very revolutionary, are they?
We are at the beginning of a revolution. It depends on two facts, both of them proved, but neither of them as yet exploited. The first is that computers can be programmed to be intelligent. The second is that they can learn from experience.
It's very hard to define intelligence, either human or machine. Usually, human intelligence is measured by carefully designed problems. Already, computers are as successful at these tests as university candidates, and sometimes even better.
This is a sliding block puzzle, not of great interest perhaps in itself, but of immense usefulness to us in our attempts to develop general problem solving and learning computer programs.
Computers are very good at doing a precisely defined job. It is difficult to produce programs that give them general abilities of the kind that is common to humans, but progress is being made. This computer has been given a number of facts. It is then asked a question which requires the power of deductive reasoning, and gets it right. Gomo Q is a quite complex oriental game. The first person to get 5 stones in a row is the winner. The experienced player will always beat the novice. Here, a good player is playing a computer which has only the simplest tactical knowledge of the game. The computer plays the cross-hatched counters. The human wins the first game easily. But even by game 3, the computer is quite hard to beat. As it examines possible moves, its memory is infallible. It will never make any move mathematically similar to one that led it to lose any previous game. But a good human player still wins. After about 16 games, the computer is virtually unbeatable. The more skilled the human opponent, the more the computer has learned, and the better player it has become.
These examples may not seem very dramatic, but they are the beginnings of something quite new, as significant as when the first wheel rolled, the first gunpowder exploded, or rocket fired, when Watt saw a kettle lid rise, when Hargreaves invented the spinning jenny, when Marconi tapped out the first message, or when Rutherford first split the atom.
One thing that computers won't be is selfish. Human beings have a certain amount of selfishness built into them in order to survive, and there's no reason why we should build that into computers.
Today, computers are mindless slaves. They are becoming immensely powerful and versatile assistants. This is bringing about the greatest revolution that the human race has ever known. A revolution which will enhance the value of human talent, but diminish the value of unskilled human labor. This revolution could lead to terrible consequences, or it could lead to the greatest advances ever for the human race. Which of these things are to happen is up to us.
Pretty interesting to take a look back, but they also, I think, bring up a lot of the questions that are still pertinent. Okay, we'll have a short break, a couple minutes. I'll just go grab a drink, and then the time is yours for whatever help you want in your studies. Yes.
I used to work at a company called Bing Labs, and we did machine learning, like classification of web pages, and we had a bunch of college students that would train. They would give us labeled data. We just BYU students we just had a whole room, like 25 of them. At any one time, I had about 60 employees. They don't do shifts, and they would just label training data or manually evaluate stuff. And we got our classifiers would do better than they would, like identifying web pages that are job pages or something. But it was like you were saying, what types of errors they make is really interesting. After Bing went out of business, and I went to work for a company in Switzerland that was a customer, and we were developing an invoice processing system. They would scan all the invoices that an insurance company would get thousands of invoices a day, all in the mail. They'd scan them and then they'd apply OCR, and then we would then take the document and classify them, because either they would get a doctor's letter or like a reimbursement or an invoice or different things. We would classify them in categories and then pull out information from them. And they had the hardest time, except the accuracy of the classifiers were about 95%, which was better than any human, like by far. But when it made a mistake, it was obvious to a human it was a mistake.
And so they felt like the classifiers were
they
terrible.
They didn't feel like it was very good, because if a human made a mistake, you'd look at it and go, oh, I see what happened.
Yeah, exactly.
But then those examples, they were really easy distinguishable when you for the classifier. But it would make mistakes, and you'd look at it and it's like,
It was obviously a dog or something. Yeah.
And it's interesting because that had a huge effect on the perceived quality. Even though the measured quality was way better. The perception was, this is not a
It's
very
true.
good.
It takes a long time for people to really understand
It was really interesting.
where machines come from.
Hey, that last video, you have a link to that?
Yeah, I can give you that.
Looks like you're done with your laptop. Are you finished with that? Or
Yeah, I think we'll be on the board.
So can I just turn the lights on and
Yeah,
project?
that would be great. Thank you.
That video is awesome.
Yeah, there's actually three. That's just the third part or half of the third part.
Those terminals, pretty good.
Yeah, it's pretty awesome. We have time for your questions. A whole nother hour. And then TA office hours if you want. So ask away. So these can be either homework problems you still have questions about even with the solutions posted, or stuff from the practice final or practice midterm, stuff from the midterm, topics you'd like me to go over again, any of these types of things.
And also one homework question, it says that depth first search sometimes can be better than A-star search. I think it's lucky, so how can it be identified?
Okay, so the question is about, I think it was a question on the midterm. Let me pull up, just be looking at it so I get the... Okay, so this was a true-false question from the midterm, and it said, depth-first search always expands at least as many nodes as A-star search with an admissible heuristic. Right? So this is basically asking about, so we saw that A-star search is optimal among optimal algorithms, right? So it will expand the fewest number of nodes possible when used with a consistent heuristic. Depth-first search is not an optimal algorithm, right? So we could come up, so for example, right, so we could have some state space like this, and depth first with, let's say, heuristics of 0, 0, 10, and let's see, cost of, let's see. Right, so if we have some setting like this, where this is the goal node, depth first search could just, because it doesn't care about the arc costs or the heuristic or anything, right? If it expanded the nodes in the right order, it could just expand this one and this one and be done with the search, right? Having only expanded 2 nodes. But A-star, because it guarantees optimality, it has to investigate this node and this node, right? Because they're the most promising. When they're in the queue, because they'll just have an F value of 1 plus 0 for each of those, which is going to be less than 11 here. And so A-star will expand more nodes than depth first search on this specific example. Of course, there will be other examples where depth first will do terribly, but the key point here is that A-star will expand fewer nodes than any other algorithm that's guaranteed to be optimal. So for example, breadth first search, I guess we could have another one that, So if we have a setting like this, breadth first search will look at all of these 4 nodes and then the goal node, whereas A star won't look at this node over here, for example. So A star will do better than breadth first, and it can never do worse than breadth first, because breadth first also guarantees optimality. So, yeah, the basic idea is that if an algorithm doesn't guarantee optimality, then there are cases where it will just get lucky, basically. But it can't always do that. So if we're talking about just comparing with A star, you really want to compare, I guess, optimal algorithms. So that's where the difference lies. Any other questions? Okay.
I have a question just regarding proofs in general. So maybe if we go over the number 6 in the midterm, the kind of proof of the A star.
Okay, so this is a good question. So this was question 6 from the midterm. So this says we've created a heuristic for our problem. We'll call it HC. And we're really excited about this heuristic, but then we realize, as we're analyzing it, that it's not admissible, which is too bad, because then A star is no longer optimal, right? But it has a really unique relationship to the true best cost for any node, is that it's always less than or equal to to the actual best cost plus C, right? And so before we throw up our hands and try to find a new admissible heuristic, we decide we want to analyze and see how poorly can A star do in this setting. Okay? So the question specifically wants to have us prove, let's see, that if we run A star with this heuristic, HC, that the cost of the solution returned by the search algorithm will not exceed that of the optimal solution by more than C. Right? So we're going to have some solution. So the solution with C, we want to prove that it's less than or equal to basically C star, which is the cost of the optimal solution, plus C. Right? So we're trying to prove basically an inequality, and often a very easy way, or an easier way to do this, is to prove proof by contradiction. Right? So you say the only way that this statement would be not true is if we ever had a case where the solution with C was greater than C star plus C. Right? So we're going to say, let's look at a case where the algorithm actually does this and prove that it can never happen. So if we prove that this can never happen, then basically we've proven this statement, right? Which is what we're asked to do. So in general, so that is a general proof technique, is typically pretty good. This is mixing. So we'll basically start, so we say we have some goal node. Let's call it G2. And we have that, let's see. Okay. And the cost of getting to G2, we're going to assume is greater than C star plus C. So basically, we say, okay, there's this node G2 in the fringe. The cost of getting there was greater than C star plus C. We want to prove that we will never expand this node. Because if the only way we could ever have this statement be true is if we expanded this node. So if we can prove that this node will never be expanded, then we've proved the desired result, right? So any questions about just the general approach before we delve in? Okay, so first we're going to say, let's go through this. Okay, so let's think about a node. So let's say there's we know that at any point, if there is a solution, that there has to be some node in the fringe that's on the path to that solution, right? So let's call that node n. Well, we know that f of n in our search will be equal to g of n plus hc of n, right? So this is just by definition of how A star orders the nodes in the fringe with this evaluation function. Right? Since by definition of HC, we know that this is less than or equal to right? Because HC is less than or equal to H star of n plus C. Okay? And now, because this node is on the optimal path, the cost of getting there plus the optimal cost of getting to the goal from this node is exactly equal to C star, right? Right, so these two lines are equal. Does everyone see that? It's kind of probably the more crucial step. So because n is on the path to the goal node, the cost of getting there plus the plus the cost of the optimal heuristic to the goal equals C star. So what we have is that the evaluation function of this node is less than or equal to C star plus C. Right? So then, if we want to compare this, so we really want to compare f of n and f of g2. So g of g2 is greater than C star plus C. We assume that our other heuristic is actually a heuristic, so that it has so its heuristic value is 0. So we didn't specify this in the statement, but you're welcome to assume either way. So if hc of n is 0 at goal nodes, then f of g2 will be exactly equal to g of g2. When we know that g of g2, by assumption, is greater than C star plus C, we know that we just showed that f of n is less than or equal to C star plus C. So A star will select n for expansion before it will expand g2. Right? And then after it expands n, there will still be another node on the goal path, and so we can apply this. So this will, as long as there's a node on the goal path, which will always be true until we've either finished our search or if there's no solution. But if there's no solution, then we're not worried about the optimality of the solution we find because we won't find one. So does that make sense? So we've proven that this, sorry, actually just a less than. So f of n is less than f of g2, so A star will select n for expansion next and not g2. So if we have a node g2, to summarize at a high level, so we want to prove that the solution we find will be less than or equal to the cost of the optimal solution plus C. Right? The only way that this would be untrue is if we found a solution that had a greater cost than this, right? The only way we can find a solution with a greater cost than this is to expand a goal node that has a greater cost than this. So we say, let's assume we have some goal node that has a greater cost than that. And we're wondering, are we going to expand this? So we say, well, there's going to be some other node that lies on the path to the optimal solution. And this node will actually have a lower evaluation function than this suboptimal goal that we found, and so we will not expand this the suboptimal goal. So we just proved that this could never happen. And so, because this can never happen, then the only other thing that the only other relation that the solution can have to this is to be less than or equal to. Any questions about that? So this is basically the exact same idea as just the proof that A star finds the optimal solution, right? Except we just have this plus C in here. So without the plus C, then we just have an admissible heuristic, and we're just trying to prove that the solution we return will never be greater than the optimal solution. Okay. That's a good question. Any questions about that or other questions?
Sorry, if you don't mind, can you say the last part? So, are we doing contradiction proof here, or something else? I'm not seeing the last part.
So it's not. I'm not sure if it falls exactly into the definition of a proof by contradiction. Basically, I don't know if this is even a terminology, but proof by. Well, I mean, we could tweak it just a little bit and make it a proof by contradiction, right? So we say, okay, let's assume that we return a solution that's greater than C star plus C, right? Well, for that to have happened, we would have had to have expanded a goal node that had a cost greater than C star plus C, right? So assuming that that happened, well, let's look at this node. And so then here's the contradiction, right? We had another node in the fringe that had a smaller evaluation than the goal node, right? So the contradiction is this goal node that we expanded couldn't have been expanded because it wasn't the lowest cost node in the fringe. So then there's the contradiction, which means that our initial assumption must have been false, and the solution we returned had to have been less than or equal to. So, I mean, it's basically that idea, right? Of just proving that the only way this could be false is impossible. That's a good question, though. Yeah.
Question in the midterm. Question number 5, letter C. It's about constructive connected regions with A squares. I don't understand the term tree structured and not tree structured. What does it mean?
Oh, okay. So this is just referring to. So tree structured is basically a graph without cycles in it. So we want something like. So something like that would be tree structured, right? But if we had like something like that is no longer tree structured. So in the problem we were taking these domino regions, right, and we were constructing constraints. So there was the two different ways of formulating the problem. The second one was right. So if we had a region like this, we'd have constraints that this one had to take on a value of this one could take on a value of this one or this one. Right, so our variables were these squares, and the values they could take on were which partner am I covered by a domino with. And so if we were to draw that, we would have basically the four different variables, and then they're connected with other variables with whom they are constrained. Right? So in this case, we would just have these connections, and that's a tree structure. Like it's a tree graph. But if we had a different so let's say we have a region like this. Now we have the constraint graph will look like this, and this is no longer a tree. So that was the basic idea behind that. It's not super complicated. So. Good question, though. Any other questions? Yeah, so that was number 4, part C from the midterm. Anything else?
Well, it's just that I'm at homework 5, but I was still wondering about in that homework about the terminal condition. It was I don't remember which problem. I think it was problem 2.
Right. With the robot moving?
Yeah, B and C.
Okay, let me just pull it up and we'll...
That's problem 3.
Okay, so... So the setting is this. We have a robot that's at right here. And we have a region 3 wide and 4 tall. So we have a robot, and so its movements, if we give it the command right, it can move either, let's see, just double check on that. Okay. Okay. So if we execute right, it'll either end up here, 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 or it'll stay where it is. Right? So there's uncertainty in the actual action that gets executed. And then our sensor is also uncertain, right? So if we're at some point here, then it could return here, 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 or here as the possible places that we are. Right? So the problem is we want to come up with so obviously by executing the action right, we're going to progress towards this goal point, and we want to come up with a terminating condition that will allow us to take our sensor values that we're getting and actually stop in the goal location. Right? So since we can pretty quickly look at like how far off could we be if we just keep executing right. I think it goes. So this shows, this isn't the solutions. Sec. Yeah. So this shows all of the places that the robot could possibly be. So we can see that as it just keeps executing right. So we can see that it eventually has to go through the goal area. Like there's no way it can miss it. So the question just is, what type of terminating condition can we come up with? So let's think about a couple of them. We won't really worry about the J component of the sensor because we know that we know that for any of these 3 eyes, well, I guess as long as we catch it right here at 0 or 1, that we will be within the right J restriction. So let's just examine a couple possible ones, right? So the first point when it could be in the goal state is at 0. So what if we set the termination condition to just be, stop when the sensor says 0? Right, well, this is obviously not going to work because the sensor could tell us 0 when we're right here, still 1 square away. So we can't use that. So let's say, okay, well, what if we say stop when the sensor tells us 1? Right? This is another possibility. So that could work if the sensor tells us 1 here, but we're not guaranteed that the sensor will actually ever tell us 1. Right? When we're right here, it could tell us 0. When we're right here, it could tell us 0. And when we get right here, it could tell us 2, 3. Right? It could just skip 1. So if we just say stop when the sensor says 1, and the sensor never says 1, then we're toast. So the solution basically is to stop the first time the sensor gives you something greater than 0. Right? So let's just think through. I guess the solution talks about the answer in a little bit more depth. The basic idea is this, right? So as we're coming along, when we're here, we can't get so we needed to prove what were the okay, so we have to prove that if it did not stop, it would eventually reach the goal. That our terminating condition can't make the robot stop before we reach the goal, and that our terminating condition can't let the robot leave the goal. Right? So just with these lines, we've seen that if we don't stop it, it will eventually get to the goal, right?
The rectangle, should that be -5 to the 5, or is that something else that you're drawing?
Maybe I just counted wrong. Is it 5?
The solution, the goal that it wants to get into is from -5 to 5.
Okay, yeah, that should be 5. I just looked wrong at the thing and thought it was 4. Okay. Okay, good point. Okay, so we will eventually get into the goal. We've shown that because the robot, even if it does the worst control it can, it'll get there. So could we make the robot stop before we get to the goal, right? Well, here the sensor could only give us a reading of -2. Here it could only give us a reading of -1. Here it could only give us a reading of 0. So if our termination, if we stop, let's see. So we want to stop when I is greater than 0. So the sensor returns I greater than 0. So right here, the largest I that the sensor could return is, so for anywhere here, is 0. So we won't stop. So we can't possibly stop there. For here, okay, so it couldn't stop us before, because if we get here, then we're in. So we just showed that it can't stop. We can't stop before we get to the goal. So now we need to show that it won't let us leave the goal. Right? Well, so right here we could get a reading of -1. And then we will eventually move to 1. And at this point we'll either get a reading of 0, 1, or 2 for our I. So if we get a reading of 0, we also won't stop. Right? But then once we get here, we either get 1, 2, or 3. And so the furthest we can get, at this point, we will have to have stopped by 2. Right? And so when we go up the whole region, so we can't stop before 0, and we can't stop, and we will stop if we get to 2, because the sensor will have to give us something greater than 0. And so this whole region is within the goal. So basically we're guaranteed to stop in the goal with that here.
So that terminating condition works. But one little addition that makes it absolutely optimal is if I is greater than 0 or I equals 0 and j is greater than 3. J greater than or equal to 3. Because when you're at that spot, if you're right, if the sensor says I equals 0 and j equals 3,
Mm-hmm.
so that would be...
because it couldn't happen right here. but
Yeah, it couldn't be. Yeah, it would have to be in the goal at that point.
yeah. So this isn't necessarily the only. I mean, there's definitely modifications we could do to this, but this is one that would work. Okay. So then the next question was let's modify the situation by moving the robot back 2 spots. Is that right? So now this. So the robot is still guaranteed to be in the goal at some point, right? Because even in the worst case, it'll be in the goal for 1 point. But the problem is that we won't ever be able to actually know that the robot is in the goal. So let's look at a -1 plus 4. Okay, so let's say that the robot's right here after doing right, and that the sensor's told it right where it is. Okay, let me just make sure. Okay, so then let's say it executes another right move. Well, then it's either going to be here, here, or here, which is all in the goal, or it could stay here. Okay, so let's assume that the robot actually reached the goal right here, but its sensor returns -1 plus 5. But the sensor returns this point right here. At this point. Okay. So at this point, if the robot actually moved there, and we get this sensor reading, now this sensor reading narrows it down to where we either are in this state or in this state, right? So the belief state contains those 2 points. And so any terminating condition that stops us at this point will necessarily stop us sometimes in this point as well, because it won't be able to distinguish between these 2. So if we decide to stop once we get this sensor reading, then we could stop here, which would not be correct because we're not in the goal yet. And if we don't stop there, then we could execute another move and end up right here, and now we're out of the goal forever. Possibly. So this is just an example of a sequence of moves that the robot could do for which there's no terminating condition that's guaranteed to be able to stop it in the goal. And that, since that's a totally possible sequence of moves and sensor readings, then there's nothing you can do in this case. So try to fix your sensor and make it better. It's a good question, though. Any other questions? Been good? Hopefully.
Will the format be similar to the midterm?
Yeah, so asked about the format of the final. It will be similar, so we'll have some true-false questions, some short answer / kind of simple problems, and then some longer problems. Still deciding on the exact number. There'll be more of each of those than we're on the midterm because we have more time. But once I settle on the final set of questions, then we'll let you know how many there are. And I'm hoping to be able to have enough questions so that you can still kind of choose one not to do on some of the sections. I think that's nice to give you some flexibility. Yeah. Anything else?
Topics that we saw after the midterm, is it okay just to study with the homeworks and the problems you gave us?
Mm-hmm. Yeah, that'll be a good study point. You'll still All the topics that we touched on in the review session last time that I mentioned are still kind of fair game. A good rule of thumb, I think, is if you haven't seen a homework style problem, then you probably won't get a homework style problem on the exam. But there's lots of things that are fair game for true false and kind of short answer stuff that you that you'll be expected to know. But I'm not a fan of springing a whole new in-depth question about something on you that you haven't ever seen before. So. So definitely, if you do that, if you look at the homeworks and the practice problems, you'll be able to handle any long question that you get. Any other questions? Okay. Well, sounds like a good time to end then. We'll still be around here after class if any of you have questions. If any of you out there listening online or watching this have questions, feel free to email. Try to be pretty good about responding quickly, especially as we're drawing close to the end time of the quarter. So good luck in your studies, and we'll see you Friday.